Okay, so let's start with our discussion today, and I think the panel discussion set up the correct stage for me. That so the overall discussion was that Wi-Fi 7 multi-link operation is where we are going to see the benefits. Okay, so I am here to see that what benefits it provides. So this is a collaborative work with University of Naples, Italy, from Stefano and Pascal, and this work has mostly been done by my student Jagritis, he is present here, and my BTech student Srimant. Okay. So this is the outline of my today's talk. First I am going to talk about the problem statement, then the analysis has been done in simulation. I am going to talk about my simulation setup, results, some root cause analysis, some solution approach and future work. So MLO, as you know, expected to provide higher throughput and significantly reduce latency. So here are some work which says that MLO should improve the 95th latency by about 78% and average latency by 69% and throughput by 2 times. So our work comes into here. So I don't know what's happening. Okay, fine. So we checked if this claim holds true in a real Wi-Fi network, and what we use to represent a real Wi-Fi network is NS3 and NS3.40 version specifically. So I am going to talk about my setup. So the simulation setup is the following, that we have some simulation time of 10 seconds. We have 3 links and we have aggregation enabled, and number of stations are from 10 to 40. This one is about 40 stations. And so the channel width is 40 megahertz on each of the links. The total offered load is 280 Mbps. So therefore, for each station we have a load of 7 Mbps. So we initially start with when the channel is perfect, that is ideal channel. There are no channel induced losses that are there, no loss model, no fading model. It's a perfect channel that can be there. And here are some abbreviation, that single link, double link 1 which is 2.4 plus 5, double link 2 5 plus 6, triple link 2.4, 5 and 6. So this graph is everybody's dream, that we see that the throughput, this is single link, double link 1, double link 2 and triple link. Let's get familiar with this nomenclature because this is what I am going to use now. So we can see that the throughput is close to the offered load here. The offered load was 280 Mbps. So here the throughput does not double or triple because I have limited my offered load, which is close to the single link saturation. And the single link does not go to saturation, does not go to offered load because of some simulation induced overhead, but it does pretty well. Now let us see in terms of latency. So let us again get used to this sort of plot. Y-axis plots end-to-end latency and x-axis shows 50th, 90th, 99th and 100th. So while we talk about latency, we either talk about median, we talk about average. So I am going to talk about the latency distribution. So we see that 50th latency, this is single link versus multiple links. Absolutely fantastically it is doing, it is reducing the latency. I have some numbers to back up. Median latency reduction by 90%, tail latency by about 90%, so everything as expected. Now I introduce some complexity. So it's complete downlink. Now in earlier case I had just only one access category which was best effort. Now I introduce best effort, voice and video. Still it is downlink, and now I see, and so this is UDP traffic. I see that the throughput although has increased in multiple links, but if you look closely it is about 75 Mbps over here, which is much less than the offered load, and this is because that now I have 3 different access categories, and these 3 access categories have different contents and parameters. So this this slide is a little bit busy slide. There are 3 access categories. These 3 access categories have different contents and parameters. So as you can see that voice has 3, CW min 3, CW max 7. So as a result, if we looked at the throughput that best effort was getting, video was getting and so on, and if you see that best effort got a very little fraction of throughput, most of the time voice and video was transmitting. So as a result, because there was internal collision amongst the access categories, as a result my throughput was lesser. Now I looked at latency, so we see that the latency reduces, but see, the latency reduction is not that significant when we saw with one access category, but yet there are some numbers, it tells that yes, latency reduces. So I will summarize UDP result that for DL traffic with only one access category, absolutely fantastic, latency reduction significant, throughput increase. With 3 access categories, throughput still increases, but the latency reduction not significant. Okay? Now I will move on to TCP traffic, because most of the internet traffic is anyway TCP. And let me remind you that in TCP, we have TCP data in the downlink direction and TCP acknowledgement in the uplink direction if you are downloading some TCP data. If it is in the uplink, then similarly, so the point to note here is that even in TCP's case, even if the data is one direction, still acknowledgement will be there in the opposite direction. And TCP is sensitive to out of order packets, and why I am telling this? Because with multiple links, there might be different latency characteristics of the links. Hence, the latencies might be different across 2 links, and TCP might be very sensitive to these sort of changes. So we considered lots of scenarios and did a thorough evaluation about that perfect channel, lossy channel, one access category, multiple access categories, parts, and dense deployments. Both DL traffic only, uplink traffic only, and both DL and uplink traffic. So I am going to talk about that simple category first, that one access category, again ideal channel and dense deployment and only DL traffic. So this I am going to contradict with whatever we have seen in case of UDP. So in TCP, we see that the throughput is lesser than whatever we got with UDP, although with multiple links the throughput increases. Okay? And this lowering of throughput is because of overhead due to TCP acknowledgements. Now when I see latency reduction, yes, the latency reduces. So look at the scale, it is actually, so I am again going to remind you that x-axis is the percentiles, y-axis is the end-to-end latency. And I see that the latency reduction is not very significant, but it does reduce. Okay? And this is because that there are now some collisions being introduced due to TCP acknowledgements, which I am going to talk about. So now we introduce some complexity. Okay? I am no longer ideal channel, so it's a lossy channel, realistic network, and we used a rate adaptation algorithm, which is Minstrel HT, and we have loss model and fading model. So I am going to talk about a result where we had 3 access categories, and it says parts deployment, about 10 stations are there, and the stations are doing DL plus UL. So same graph, throughput, downlink and uplink, I see that across with multiple links the throughput does increase. Okay? Now this is interesting. Okay? Now I see the latency distribution. This is what, since I have now traffic both in the downlink and uplink direction, I am plotting them separately. So downlink and uplink. Now look at that this 90th percentile in case of downlink. See that with multiple links my latency increases compared to single link. And if you look at uplink, the 100th percentile, the latency increases. So this is like we are completely surprised. We can understand the latency reduction can be not that significant, but how can it increase? So then I looked at TCP statistics. Okay? So this TCP round trip time, this is for downlink and this is for uplink. And this is a distribution. So how to read a distribution graph? So this is median, and this is the 25th percentile, 75th percentile, and the outliers that are coming. Now if we look closely, we see that compared to single link, the RTT, the higher order percentiles are increasing. Okay? Now we looked at some more TCP statistics like TCP retransmission. So I was telling that because that there will be latency differences into multiple links, we might see some out of order packets being happening because TCP is sensitive to in order packets. So we looked at how many TCP retransmissions are happening and out of order percentages, and see that it is increasing with number of links. Okay? So then we thought that is this because some one particular case this happened. So then we did lots of simulations. So this one with dense 40 stations, 3 access categories, downlink plus uplink. So again here, similar sort of observations that the throughput increases with links, the end-to-end latency increases. So we can see that here 98, 100 percentile both for downlink and uplink increases. And in terms of RTT, interestingly see for this uplink, this green curve, the median RTT increases. Okay? So which is like a complete contradiction to that MLO is expected to achieve. So then we looked at retransmissions and out of order percentages, and the same was holding true. So then I was having a discussion with Srikant, and Srikant said maybe that this is because you are using homogeneous links and so on. Is it because that there is some specific configuration? So then we had this thought process in our mind that homogeneous links are going to see similar latency characteristics. Heterogeneous are going to see this problem more. And then we validated this, that we use heterogeneous links that 20, 80, 160 on 2.4, 5 and 6. So the offer load accordingly has increased because when you are taking single link, we are taking the 80 megahertz. So again the similar observations that the throughput increases, and these are my end-to-end latency plots. And now we see that this increase in end-to-end latency is even more, and that is expected. Because if there are homogeneous links, then these links are in simulation, ideally they are similar, whether 2.4, 5 and 6. When they are heterogeneous, more such latency differences are coming out of different channel bandwidths I have. Similarly, retransmissions and out of order packets also, I am seeing that it is increasing. So to summarize, the TCP traffic analysis that we did, that with only one axis category, the latency reduction is not significant, but latency reduction is there. And with 3 axis categories, higher percentile end-to-end latency increases with link, and TCP RTT higher percentile increases with link, TCP retransmissions out of order percentages increases. With dense network, this was about sparse network. In a dense network, again all the things same hold true. Also the median TCP RTT median increases, not only the higher order percentiles. And in case of heterogeneous network, this increase is more pronounced. Okay? So with this, we said that these observations are contradiction to what MLO is expected to achieve. So let's do some root cause analysis, that what is causing this sort of increase. So then my students, she looked into NS3 code and got to some traces, and looked at there are some transmission failures happening at the access point and at the stations. So this was collected using negatively act AMPDU trace in NS3, which reports that AMPDUs that are negatively acknowledged via block act. And we said, why would there be a negative block acknowledgement? So then we looked at PSDU response timeouts. So this is the y-axis is how many times these PSDU response timeouts are happening for single, double and triple links. And we see that PSDU response timeouts are happening more with multiple links, and this is happening because the PSDUs whose response were not received before the timeout. That means the acknowledgement was not received. Okay? So then, we plotted a graph where we looked at the number of PSDU response timeouts are happening, and side by side we looked at the throughput graph or the number of packets that are being received across multiple links. And as we expected, right, that MLO is expected to improve throughput. So we see that more number of received packets when we have multiple links. Okay, but why am I telling this? So this has a different meaning, that more number of packets that are being received, that means more TCP acknowledgements will be generated. More TCP acknowledgements will be generated, that means more contention will happen with the downlink TCP date and uplink TCP acknowledgement. So it's a double sword problem that we have created. So we are expected to improve throughput, because of which I am pumping more traffic. More traffic is creating me more contention in terms of TCP. So number of received packets increase with more number of links, and more TCP acknowledgements need to be transmitted as a result of this, and therefore there is a collision due to bidirectional nature of the TCP. Okay? So then we said, okay, let us see that what can we do about it. And then our objective was basically, at this point we zeroed down on the problem, that collision. Somehow when I started my PhD, that time also problem was collision, that was in Wi-Fi G, like 802.11g, and now I am talking about Wi-Fi 7, still collision. I don't know why we have not been able to solve this collision problem. Anyway, so I know why, because it's a distributed MAC protocol. So all STAs are containing on the same link, because even if MLO, but everybody is containing in all three links if we have that at their exposure. So we said let's utilize some TID to link mapping. So then I can restrict a set of stations into a set of links, and that way I can restrict the contention or collision. So then we can map a set of specific TIDs to a specific links, and stations of that TIDs will be active only on that link. Suppose I say best effort only on link 1, voice on link 2, video on link 3, this type of separation I do. And then we did some simulations one second with this TID to link mapping. So this graph, throughput graph again, without TID to link mapping, with TID to link mapping. So we can see that the throughput increases with multiple links, and the throughput increases more with TID to link mapping than without, and of course with compared to single link the throughput increases. All good news. Let's see the latency, because this is what we are more interested about. This time I changed the presentation of graph a little bit, because I am looking at median and max separately to more zoom into the result. So we see that this is without TID to link mapping, and this is with TID to link mapping. This is the median end-to-end latency, and this is maximum end-to-end latency. So first of all, without TID to link mapping, we are doing better in terms of this DL2, TL, and for max latency we are doing really better. Okay, and so but that wouldn't suffice, right? We have to compare with respect to single link, because why do I bother utilizing multiple links? So we see that with respect to single link, we are doing better, that our latencies are reducing. Except one case. So then we looked at again the TCP RTT. So this RTT again I will tell this graph: single link, double link, no mapping, double link mapping, double link 2 no mapping, double link 2 mapping, triple link no mapping, triple link mapping. And you can, if you compare no mapping with mapping, you can see that the boxes have reduced now. Okay, the latencies have reduced. And with compared to single link also, our latencies has more or like it does not solve the problem completely, but we see to some extent the latency has decreased. Okay. So then we looked at those failures that they were happening earlier, has this reduced. So remember those are failures I was talking about that we collected at the stations and the APs, and we see that they have reduced both at the AP side and at the station side with mapping and without mapping. And we looked at those TCP statistics, retransmissions and out of order percentages. They are more compared to single link, but they have of course reduced from without a mapping. Okay, and this problem with more compared to single link, it is always bound to increase because we are pumping more traffic. So to summarize, I have exactly 2 minutes. Sure. So to summarize, so our analysis was that we said that how exactly MLO interplays with TCP, and then we saw that end-to-end latency with MLO can be similar to SLO if like you have a pure channel and it's a downlink, like it can still reduce or it can be at max be same if there are collision across access categories, which is the internal collision I was talking about, but it can sometimes increase with MLO, and that was due to external collisions. So therefore, this TID to link mapping solution that I talked about, it tells that how reducing collisions can help the MLO flows to realize the true potential of MLO. So on that line, so TID to link mapping was just an hypothesis to tell that if you can restrict the number of flows contending at a time on the links, then there is a promise. So this gives the future work that we should be able to come up with some link scheduling strategies. In the panel discussions also, there was this discussion that what sort of scheduling is important. So this link scheduling algorithm is needed such that we can design this optimal TID to link mapping before. And this was kind of a static mapping we did, right? So this sort of link scheduling strategy needs to come up with such that we can give that which set of flows to ascend to which links and so on. And so there was an interesting discussion we are having that WFDMA did not see any future, but for some reason I believe that we might be able to find some solutions where, some scenarios where WFDMA might see its benefits, and that could be TCP acts, that we are seeing the TCP acts were contending with the TCP data. And that's the reason mostly that in case of downlink the latency was still increasing. So we can send the TCP acts in a WFDMA fashion, right? Those are small packets. Ideally WFDMA should do better in those cases. So this is again to something that we will explore in future and maybe talk sometime at future Wi-Fi case.
Thank you.
Okay.
We have time for questions. Please put up your hand. There's a question there. Yeah, hold on. Get the mic. Whoever got the mic, ask.
Yeah, the final, here.
Yeah.
So the final set of results that you had showed with TID to link mapping, is there any difference between homogeneous and heterogeneous links getting used in the final case that you had shown? And is there, like for the other alternative solutions also, do you really feel that homogeneous and heterogeneous links will actually make a difference? Because in most of the deployments, we have heterogeneous links being used, right? So what are your thoughts on that?
Sure. So I think the heterogeneous deployments are going to, in terms of TCP, it is going to create more such out of order packets. Okay, and as a result the RTT is going to increase now. So this sort of TID to link mapping is a solution that can be applied to both. I feel the heterogeneous will see little bit lesser improvements than homogeneous one.
When we had multiple links, like the results in what you have showed, what type of MLO mode was implemented? Is that EMLSR or STR?
That's a very good question. I should have mentioned that that is STR mode. NST has STR mode, and by the way, the scheduler is greedy scheduler. Whenever the link wins the contention, that time it transmits on that link.
Okay, if it is STR MLMR, when we said about TCP acts being waiting and creating an overhead, we can simultaneously transmit when the AP is transmitting the data, and we can transmit the acts also, right? Since it is simultaneous TX RX.
Sure.
Cannot be.
But then, like, whom you will be sending the acknowledgements to the AP, right? So the contention you are not going to go away with. You anyway Wi-Fi, any kind of feature that is coming on top of CSMA, you have to anyway content. That nobody is able to get away with.
One short question. So, how was the latency measured in these experiments? Is it with this NS3 simulator, or is there a different method to measure them?
So this is NS3 simulator. So I talked about two different latencies, TCP RTT and end-to-end latency. So end-to-end latency is the packet got generated at the application layer at the sender, packet got received at the application layer at the receiver. That is the end-to-end latency. And TCP RTT is TCP round trip time. TCP packet got generated when the acknowledgement got back, the difference between the packet generation and the acknowledgement reception time.
Yeah, you go ahead.
Yeah, so how you explain this TID to link mapping will reduce this external collisions, but still TCP is still the bidirectional nature is still there. So how it is actually reducing this external collisions?
Oh, very good question. So bidirectional we cannot get away with, right? So the TID to link mapping, all it says that collision was the main problem. All I am trying to is limiting the collision across the number. So I am limiting the number of stations that are active on a link by utilizing TID to link mapping. So kind of an soft isolation I have on top of CSMA.
Last question, Sheila.
Yeah, I have a question on NS3 simulator. I suppose you have used this file-layer abstraction. What PLA techniques are supported by NS3? And in your simulation, which PLA technique was used?
What technique, sorry?
File-layer abstraction. Which techniques are supported by NS3, and in your simulation, what is it used? It is ESM or RBIR?
So I don't think I am able to understand your question perfectly, but it's the STR mode on top of which it runs. So the physical layer is abstracted out in NS3, and then this is the MAC level simulations I am talking about.
Okay, thanks Mukulika.